So by now, you probably realize that I love lists and I love three-step processes. And as far as solving force problems, I have another three-step process for you. And my guarantee is that if you follow this every time, A, you'll have a much better understanding of what's actually going on in a problem. And you will be, let's say, 75% more likely to get the answer correct. Okay? So even if it feels cumbersome and clunky at first, practice this three-step process for forces, and these things will start to become second nature for you, okay? And I'll show you. So we have three simple steps here. Simplest steps for every force problem. Okay, so step one, okay, the first step is always to draw a free body diagram, okay? If you draw a free body diagram, you can really come up with your Newton's force laws equations just by reading it off the free body diagram. And I'll show you what I mean by that in a second. But we're going to draw a free body diagram, always the first step here. Okay? In other words, a force diagram, which you guys know. Second, you use that free body diagram to write Newton's second law. So you're summing all your forces. Okay? Now, if this is a one-dimensional problem, this is fine, right? But if it's a two-dimensional problem, you have to remember that force is a vector, and truthfully, this is the summation of forces in x equals m times the x component of the acceleration, or the sum of the components in y equals m times the a component of the acceleration, okay? So this is 1D, and this over here is 2D. And we're going to do examples of both, so don't worry about that right now. Third, you just solve the variable, guys. That's all you got to do. Once you have these equations, you can go ahead and solve for the variable that you're looking for, okay? And so if you guys could advance to one slide, it says the elegant locomotion of a jellyfish. I'll add a video of this in the module. But for now, we're going to apply the three-step process for every force problem, the simplest steps, in order to understand the motion of this jellyfish, okay? So it says measurements have confirmed that a certain jellyfish can generate 5.32 newtons of force while experiencing a resistive force from the water of 1.11 newtons. A, what will be a 220-gram jellyfish's acceleration through the water? And B, how fast will it be going if it's propelling itself with that acceleration for 3 seconds? Okay, let's apply our rules. Okay, number one, draw a free body diagram. Okay, so I here have a jellyfish, right? So this is going to be over here. I got a jellyfish. Okay, I don't know, something like that. Looks like a Pac-Man ghost with a bunch of tails, something like that. Okay, so I have a force being applied in the direction of its motion. We'll just call that F. Okay, and then it also has a resistive force from the water. We call the resistive force in water just drag. Okay, so I'm going to put a D down here for drag. Okay, is there any other forces? Technically, there's gravity on here, but this problem has this jellyfish operating in water without really gravity playing much of a part. Okay, we have its propelling force forward and its drag force backwards, and that's all we're really concerned about in this moment, at this problem, okay? We're going to start simple. So once we have this free body diagram, and we agree there's no more forces on here, and we've clearly drawn it, the direction matters. Direction is very, very important. We go to step two, which is sum of the forces. Now, I made this be a one-dimensional problem, okay? Everything's happening in this y dimension, okay? So I don't have to separate these guys out. I can just use this, right? So I can say the sum of my forces equals mass times acceleration. Well, what forces do I have? I got this force F going up, right? And then I have drag going down. So that's in the negative direction, so I'm going to put minus D there, right? Equals M times A. Right. Do you guys see where this is going? like part A asking for. It says, what will be the 220-gram jellyfish's acceleration? Ooh, check this out. We have acceleration, okay? We know the force because the problem gives it to us. It says it's 5.32, right? And we know the drag. The problem gives it to us. It says it's 1.11 newtons, okay? So all we got to do is sub in our stuff and solve for A. Do you guys see how simple this three-step process made this problem? Before you're like, oh my God, how do I analyze the motion of a jellyfish? It sounds all weird. But really, this really trims off all the flab and makes it a nice, simple problem. Okay, so let's put in all our guys here. So we have 5.32 minus drag, which is 1.11. Right, the mass is, they say 220-gram jellyfish, but is grams SI unit? No, kilograms is, so we got to convert that to kilograms. So it's 0.22 kilograms, right? And then we have acceleration, and I get a value of 19.1 meters per second squared. Okay? Hopefully I'm still on the screen. If I'm not, just know the acceleration that I get is 19.1. You guys can check my work, put that into your calculator. Okay? All right. The next part of the question says, how fast will it be going after propelling itself for 3 seconds? And now you might look at this guy and you'd be like, huh, how fast? I don't see velocity here anymore. This is a perfect point to not forget everything else we've learned, okay? Using force analysis, we found an acceleration, but that doesn't mean all the kinematics that we learned can go out the window, right? We can still use all that stuff that we've been learning and practicing all this time, okay? And so I am going to make some room for myself so that I can do some of that, okay? All right, and I don't have my, where are you? Let's see if I can just, yeah, do like this. Okay, this is going to be terrible, I'm sure, but hopefully me struggling is entertaining. We all know that the bloopers and the outtakes of any TV show are the best part. So I'm leaving this in here. I'm not editing this out. Okay, so how fast will we be going after 3 seconds? That sounds an awful lot like a kinematics problem, right? So let's do it. We have V1, V2, A, D, T, right? We assume it's starting from rest, so it's 0 meters per second, right? We want to find out how fast it's going after 3 seconds, so that's our question mark. A is what we just found, 19.1, right? D is, we don't care, right? And T is the time, 3 seconds, right? So I can just use my classic kinematics equation, V2 equals V1 plus AT. And so V2 is what we're solving for. V1 is 0. A is 19.1 meters per second. And then T is 3. And I get an answer of 57.4 meters per second. Okay? So don't forget your old toolbox, okay? You learned a whole bunch of cool stuff up to this point in this course. That is all available to you. In fact, it should be available to you as you move into new stuff like forces and energy, which we're getting into next week, okay? I'm going to leave it there. This is our first force problem, and when we come back to the next video, we will explore how to look at this stuff in 2 dimensions.